Time is not the same everywhere, not in space, not in distant galaxies. Right here, on Earth, on this planet, a clock at the top of a mountain runs faster than a clock at the bottom. A clock in a fast-moving airplane runs slower than a clock on the ground. And in 2010, scientists built instruments precise enough to measure the difference in the rate of time caused by lifting a clock 30 centimeters, about 1 foot, off the ground. 30 centimeters, the height of a laptop, and time ran measurably, detectably, quantifiably differently at that height compared to the floor. This is not a thought experiment. This is not science fiction. This is one of the most thoroughly tested and confirmed predictions in the history of physics. And the reason most people don't know it, the reason it feels like something out of a movie, is that the effect is so small at everyday scales that human senses cannot detect it. But it is real, and it has consequences that touch your life every single day, whether you know it or not. Stay with me, because the layers of this go to places that change how you think about what time actually is. Let's start at the beginning. In 1905, Einstein published what is now called the special theory of relativity. The core of it was a radical idea that the speed of light is constant for all observers, regardless of how fast they are moving. And the consequence of that single idea, worked out mathematically, is that time is not a fixed, universal backdrop against which events happen. Time is relative. It depends on how fast you are moving. The faster you move, the slower time passes for you relative to someone who is stationary. This is called velocity-based time dilation, and it is real. 10 years later, in 1915, Einstein published the general theory of relativity. And here, he extended the idea further. Not just velocity, gravity itself affects time. The stronger the gravitational field you are in, the slower time passes for you. A clock near a massive object, like a planet or a star or a black hole, runs slower than a clock far away from that massive object. This is called gravitational time dilation. Both effects are real, both have been measured, and both operate simultaneously in the universe, right here on Earth, right now. Here is the first way this matters in everyday life: GPS. Your GPS, in your phone, in your car, in navigation systems used by airplanes, ships, military equipment, emergency services, works by receiving signals from a network of satellites in orbit. Each satellite carries an extremely precise atomic clock. The satellite constantly broadcasts its position and the exact time according to its clock. Your receiver picks up signals from multiple satellites simultaneously, compares the tiny differences in arrival times, and calculates your position from those differences. The precision required is extraordinary. The system needs to know the time from each satellite to within a few nanoseconds, billionths of a second, to calculate your position within a few meters. If the clocks were off just a few microseconds per day, millionths of a second, the position errors would accumulate to hundreds of meters. The GPS system would become useless within hours. Now here is where relativity becomes practical engineering. Your GPS is in orbit approximately 20,000 kilometers above the Earth's surface. At that altitude, gravity is weaker than at the surface. According to general relativity, gravitational time dilation, weaker gravity means time passes faster. The satellite clocks, experiencing less gravitational pull than clocks on the ground, run faster than clocks on the surface by approximately 45 microseconds per day. At the same time, the satellites are moving at about 14,000 kilometers per hour. According to special relativity, velocity-based time dilation, moving clocks run slower relative to the ground clocks by approximately 7 microseconds per day. The net effect combining both relativistic corrections, is that the GPS satellite clocks run faster by approximately 38 microseconds per day compared to clocks on the surface. 38 microseconds of timing error per day sounds negligible. It is not. 38 microseconds of timing error per day translates to approximately 10 kilometers of position error per day. If the engineers who designed GPS had not accounted for relativistic time dilation, if they had assumed, as Newton did, that time passes at the same rate everywhere, GPS would accumulate errors of roughly 10 kilometers per day. Within weeks, the system would be useless. The engineers did account for it. They built the relativistic corrections directly into the satellite software. Every GPS satellite in orbit is running a clock that has been deliberately adjusted to compensate for the fact that relativity will cause it to run at a different rate than clocks on the ground. This is not theoretical. This is operational engineering. Relativity is baked into the infrastructure that billions of people use every single day. Now, let's talk about altitude, because this is where the story gets more personal and more strange. The gravitational time dilation effect means that time passes faster at higher altitudes, further from Earth's center of mass, than at lower altitudes. The difference is tiny at everyday scales, but it is real, it is continuous, and it is accumulating right now. A person who lives their entire life at high altitude, say in the Andes or the Himalayas, experiences time passing very slightly faster than a person who lives their entire life at sea level. By the time they die, the person at high altitude has aged, biologically, atomically, in every physical sense, very slightly more than the person at sea level. The difference over a full lifetime is measured in microseconds. You would never notice it. Your body cannot detect it, but it is there. It is real. In 2010, physicists at the National Institute of Science and Technology in the United States published a paper demonstrating that they could measure this effect at everyday scales using optical atomic clocks, the most precise timekeepers ever built. Clocks use the oscillation of atoms trapped in a lattice of laser light to measure time with extraordinary precision, the ticking of atoms. And these clocks are so precise that they can detect the difference in the rate of time caused by raising the clock by just 30 centimeters, about the height of a large book, off the ground. 30 centimeters closer to the center of the Earth means slightly stronger gravity. Slightly stronger gravity means time runs very slightly slower, and the clock can measure it. This was not a thought experiment. This was a laboratory result, published, peer-reviewed, real. The precision of these clocks have since improved further. Modern optical atomic clocks are so precise that they lose or gain less than 1 second over the entire estimated age of the universe, about 13.8 billion years. And at that level of precision, the relativistic effects of gravity become relevant even at human scales. Scientists now use these clocks to map gravitational fields by watching how fast clocks tick at different locations, a technique called relativistic geodesy. You can map the terrain of the Earth by watching how fast clocks tick at different locations. Now let's go beyond Earth for a moment, because this is where the reality of time dilation becomes genuinely unsettling. Near a black hole, the gravitational field is so intense that the effect on time is not subtle. If you were to orbit close to a stellar mass black hole, not at the event horizon, but in a stable orbit at a safe distance, time would pass significantly slower for you than for someone watching from a distance. Hours might pass for you, while years pass for someone watching from a distance.
This is not science fiction. This is the direct mathematical consequence of general relativity, and every observation we have ever made of black holes, neutron stars, and gravitational waves is consistent with these predictions. We have never found an exception, not one, in over 100 years of tests. The extreme version of this is what happens at the event horizon, the boundary of a black hole beyond which nothing can escape. At the event horizon, from the perspective of a distant observer, time dilation becomes infinite. An object falling into a black hole appears from outside to slow down and freeze at the event horizon. The clock on the falling object appears to stop. From the perspective of the object itself, it falls through normally. The asymmetry of time experienced by different observers is a fundamental feature of the universe. And then there's the question that this all eventually forces you to confront. What is time? We experience time as a flow. We feel it moving. We age in it. We remember the past and anticipate the future. Time feels like the most fundamental background condition of existence, the stage on which everything else happens. But what relativity tells us, and what over a century of experimental confirmation tells us, is that time is not a fixed background. It is a dimension, like space, that can be stretched and compressed by gravity and velocity. Different observers can measure different amounts of time passing between the same two events. There is no single universal clock ticking in the background of reality, marking the same moment for everyone, everywhere. There are only local rates of time, rates that depend on the gravitational environment and the velocity of the observer. This is not a paradox or a problem to be solved. It is just how the universe works, and it is one of the most verified facts in all of physics. But it does raise a question that stays with you once you really absorb it. If time runs faster on a mountain than at sea level, and it does, and if time runs faster for a GPS satellite than you standing on the ground, and it does, then the question of what time it really is has no single answer. Every point in space has its own rate of time. The universe is not synchronized. Reality is not happening at the same time everywhere. The feeling that there is a single now, a moment that exists simultaneously across all of space, is an illusion created by the fact that we live in one place, move at the same speed as everyone around us, and are all embedded in the same gravitational field. Step outside those conditions, go faster, go higher, go into a stronger gravitational field, and the illusion breaks. The clocks run differently. Time is not what we thought it was. And the evidence for this is in the phone in your pocket, correcting for relativistic time dilation every time you ask it where you are. The sky still hides secrets, and this is just the beginning. Subscribe to Fact Harbor for more mystery.